Hello, welcome to lesson 9. In this lesson, we are going to look at the further examples on concave and convex mirrors. We shall also look at the reflection of a parallel wide beam of light at curved mirrors. And then we shall look at the comparison of concave and parabolic mirrors. And then we shall lastly look at the determination of the focal length of a concave mirror. Let's begin by looking at further examples on concave and convex mirror. Let's look at this example. A concave mirror P of focal length 15 faces a convex mirror Q of focal length 10, placed 25 centimeters from it. An object is placed between P and Q at a distance 20 centimeters from P. Determine the distance from Q of the image formed by reflection first in P and then in Q. So we want that distance, and then also we want the magnification of the image formed in one above. Let's look at that. So we have a concave mirror. You have a concave mirror. It is placed in front of a convex mirror. It is placed in front of a convex mirror at a distance of 25 centimeters apart. And then the object is placed at a distance of 20 centimeters from P. So we shall place 20 centimeters from P, but it is placed between P and Q. So it is 20 centimeters from P. And therefore the leftover here is going to be 5. 25 minus 20 gives us 5. Now we are going to draw a ray from O unto first P, which is going to be reflected and to lead to the formation of this image I1. But remember, there is this mirror here. So as it is going to I1, it meets this mirror. That means that this I1 is going to be a virtual image. That would be the first position of the image, but it is not, that image is not going to be formed, but to be formed at I1, the first image. So the first image will be formed at I1, but it's not going to be formed there. So we are going to have this other reflection, which is going to be a divergence away from, and then we shall lead to it will lead to the formation of this image I2. So we shall have the final image as I2. That's going to be a final image. So this I1 is going to be like the intermediate image. Now we are going to apply the mirror formula at each of the mirrors. So we are going to begin by looking at the concave mirror and apply the mirror formula there. So if you look at the action of the concave mirror and then we apply the mirror formula, remember our U is going to be 20, the focal length is 15, so 1 over V is going to be 1 over 15 minus 1 over 20, and therefore we shall get our V as 60 centimeters. So that means that DC, if this mirror was not there, the image would be real and would be at a distance of 60 centimeters. So I1 is going to be 60 centimeters from P. Now we want to get the distance from Q. From Q, this is Q. So if I want to get the distance from Q where the image is going to be formed, that's what we are going to look for. So first of all, we are now going to look at the action of the second mirror, because we want this I2. It's actually what we want, I2. So we are going to look at the action of the second mirror. If you are considering the action of the second mirror, we need to know that the object distance is going to be this one for the second mirror, which is actually going to be 60 minus 20 plus 5, which is 60 minus 25, which is 35. But it is virtual because it is not real. That object distance is going to be real. It's going to be virtual. So let us first get that distance, which is 35. And then now we are going to look at the action of the convex mirror. So the distance from here up to here is going to be 35, and it's going to be the object distance for the convex mirror. So it's going to be 35, and it's going to be negative. The focal length is negative 10 because it is a convex mirror. When we apply the mirror formula on that, we shall have our 1 over V is equal to 1 over F minus 1 over U, which is going to be 1 over negative 10 minus 1 over negative 35, and therefore our V is going to be negative 14. So it means that the final image formed by this one is going to be a distance of 14 centimeters behind the mirror. The magnification also is also they want us to get magnification because we have two mirrors, if we want to get the magnification, it's going to be magnification of this mirror times the magnification of this mirror, which is magnification m1 times m2, which will give us, for m1 is v1 over u1, for m2 is v2 over u2, which will give us 60 divided by 20 times 14 divided by 35, and then we shall get 1.2. Let's go ahead and look at the reflection of parallel wide beam of light at curved mirrors. So we want to see when we have the wide beams. Those are beams far away from, we have different beams which are going to be far away from the principal focus, the principal axis, and also from the paraxial rays. So you can see these paraxial rays, these are rays which are close to the principal focus. They are always going to be formed, which are close to the principal axis, are going to be reflected through the principal focus, these ones. But then when you look at these other ones, they're going to be reflected closer. So we realize that these marginal rays, the ones which are farthest from the principal axis, are going to be reflected nearer to the pole. So the farther they are from the principal focus, from the principal axis, the nearer they are going to be closer to the pole. That's why you see these ones which are farthest are closer to the pole, and these ones are now moving away from the pole, and then these ones. So that is an important note that you're going to make there. But also we need to note that because of that they are going to be formed at different points, the images which are going to be formed are going to be blurred. They're not going to be clear. And because they're going to be blurred, this surface formed is going to be called a caustic surface. The surface here, that a caustic surface is simply that surface formed by joining the positions where the rays are going to be reflected to. So at this point, so because we are going to have an image here, another image here, another image here. So if we join those image positions, we form what we call a caustic surface. So let's make a note there, which I've talked about, that for the marginal rays, they are going to be focused closer to the pole as compared to the paraxial rays. And then also, we need to note that if there was a convex mirror, for a convex mirror, they will be appearing to be coming from some point. Yeah. So for the convex mirror, those white beams of light still would be reflected from at different directions, but they would be appearing to have been diverged from some different points. So for them, they would be, if these were the convex, they would still appear to be diverged, but from different points. Just like these ones are converging at different points, then also will be appearing to be diverging from different points. If it was a convex mirror, it would be appearing to be diverging from different points. So let's look at the comparison of concave and parabolic mirror. So we have here a concave and a parabolic. So a parabolic, you can see it is more curved. Concave is quite curved, but this is more curved. Now the comparison here is that when we place a source of light at the focal point, that light is going to be reflected parallel to each other. It's going to be reflected parallel to each other. Unlike this one, when we place a source of light at the focal point, it's going to be reflected when they are not parallel. But these ones are going to be reflected when they are parallel. So because of that, it makes there's going to be a big advantage of the parabolic mirror, or a big use for a parabolic mirror. Yeah, so we are saying that the advantage is that the advantage here is that the parabolic mirror has an advantage of reflecting light placed at the focus, that's the principal focus, parallel to the principal axis with undiminished intensity. That is the advantage there. So the use is going to be used in searchlight torches. That is going to be a big use in searchlight torches, used as reflectors in searchlight torches. Let's go ahead and also look at the determination of focal length of a concave mirror. Yeah, we have very many methods of determining the focal length of a concave mirror. In this lesson, we're going to use We are going to look at two methods. Let's look at the first method here, using a pin, which is at C. So here we shall have a setup here. So this is a concave mirror placed facing upwards on a bench, facing upwards. You place it on a bench facing upwards, and then you clamp a pin horizontally on a retort stand, such that the tip of that pin must be lying along the principal axis. Must be lying along the principal axis of this concave mirror. So we are going to use the no parallax method here. So we are going to then move the pin up and down. Remember, we have placed it horizontally, but you are going to be moving it up and down, horizontally up and down, until when the image of that pin coincides with the object. They must coincide with the object by the no parallax method, until the image of the word coincides with the object by the no parallax method. When we talk of no parallax, we mean as you are moving your eye, remember we are seeing from above, that as you are moving your eye to one direction, even the image will be seemingly moving with the eye in the same direction. They will not be moving different directions, they will be seemingly moving the same direction. That's what we call the no parallax. So we shall move the eye such that we shall move the pin horizontally up and down. Shall move it up and down. Of course, it will be horizontal, but we shall move it up and down, upwards and downwards, until when the image coincides with the object by no parallax method. And when that is attained, when they attain coincidence by no parallax, then we shall measure the distance from the pin to the table, and that distance will be r. That distance will be r. And after getting that r, we shall know that r is equal to f, and therefore f is going to be r divided by 2. That will be the focal length of that concave mirror. Now the note here I was talking about is the no parallax. At that point where there is no parallax, it means that as I move the eye to one direction, even the image seems to be moving with the eye. That is, so they'll be seemingly moving in the same direction. So actually both the object and the image will be moving in the same direction. Both the object and the image will be moving in the same direction. So if both the object and the image are moving in the same direction, it means that there is no parallax between the two. And that's why we call that method the no parallax method. Let's lastly look at the method using this illuminated object at C. So this time around we shall have the object being formed by a screen, a white sheet of paper, of course, which will be on a cardboard, and then we shall make that hole on that cardboard and then place a cross wire in between, and then we shall have a light source. So the cross wire and the light is going to be the source of it's going to be like the object. This light is going to be the object, maybe a bulb, a torch bulb. It's going to be the object, and therefore on that same, besides, just adjacent to that hole, we shall have our screen. It will be the screen, and that is going to be where the screen is. And usually we place the white sheet of paper there to make the screen. And so we shall also get our concave mirror, place it on a mirror holder, and then place it in front of the screen and the object. So we are going to move the concave mirror. We are going to move the concave mirror until when we focus the cross wire on the screen. We shall focus a cross wire on the screen. We shall get a sharp image of the cross wire on the screen. A sharp one. It must be a sharp one on the screen. So you just keep on moving this away from the object and towards the object until when you get a sharp image of the cross wires on the screen. After getting that, you measure the distance r, and that distance r is actually going to be the radius. R is the radius of curvature, so r is going to be 2f, and therefore if you want f, it's going to be r divide by 2. That is going to be the focal length of the concave mirror. Thank you for your attention. See you in the next lesson.